Sometimes in composites, you need to produce a complex one-off part on a tight budget and timescale. A couple of weeks ago, James from the Project Air channel got in touch to ask if we could help him beat the world record for the fastest jet-propelled RC car to be run at the Rossa Speed event in Wales. And so, in this video, I'm going to demonstrate some practical techniques and shortcuts that can be used to produce complex one-off prototype parts like this in just a few days for a fraction of the usual cost. I'm Paul from Easy Composites. Let's dive straight into it. Before the composites work could be started, we needed a design for the chassis. And so, having gone through the requirements with James, I handed the CAD work over to our very own aerospace engineer, Edwin, who got to work modelling a super stiff carbon fibre monocoque for the car. Looking at the CAD then, we've got this long tubular form which would necessitate having a split mould. We've also got some really tight detailed areas and some fairly restricted access, all of which would generally mean pre-preg as being the most obvious choice. But that would give us a problem. Pre-preg parts need high temperature moulds, and high temperature moulds generally need epoxy patterns. All of this is expensive and very time consuming, which is simply time and budget that we don't have for this project. Not to mention serious overkill for a one-off part like this. So instead, we're going to resin infuse it. If all goes well, this has to be the most awkward and complex resin infusion I've ever done for a video, but that should make things quite interesting. One of the most unusual shortcuts I'm taking on this project is to not start by machining a pattern and then use the pattern to go on to make a production mould like you normally would. Instead, I'm going to directly machine the mould from model board. I can do this in this case because this project is a one-off and the mould only needs to survive 1 or 2 releases. And the resin infusion process can be done at room temperature, so in theory, directly machining the moulds from board should work. With this in mind, in design terms, instead of machining the positive shape, we'll be machining the negative. This means drawing our board stock and then subtracting the finished shape from it. Being a split mould, this process is done for both sides and some holes for alignment dowels are added. Separate moulds are then also generated for the nose cone and top hatch, and then the tool paths are generated for the CNC machine. If you'd like more information on CAD techniques for composite tooling, we have produced some detailed videos on this topic. But bear in mind when watching these that they will involve machining a positive pattern rather than a negative mould like we'll be doing in this video. As well as directly machining the moulds rather than patterns, another cost saver on this project is to use a relatively low density PU model board. In this case, it's our PU240, rather than the higher density PU or even epoxy boards that would typically be used in patterns. Not only is a low density PU board like this a fraction of the price of an epoxy tooling board like EB700, which is just as well as the moulds for this massive RC car are almost 1.5 meters long. It also machines and sands far more quickly, and so to slash the machining time down from over a day to just a few hours, we can use an aggressive roughing strategy and a large step over, omit all the fine finishing passes in favour of just doing some hand sanding. These are the moulds straight from the machine, and being done in low density model board does mean that they're actually very lightweight. Now looking at these, you'll see we do have some distinct tooling marks. Now this is down to the very aggressive fast machining strategy we used, but this material does sand very, very easily. So we're going to set to now and just spend a few minutes getting these knocked out. Fortunately, low density board like this sands very quickly, and so whilst this would be a very time consuming operation on a higher density tooling board, the steps from the rough machining operation flat away by hand very, very quickly, hours quicker than a smaller step over would have taken on the machine. Although we've now got a pretty smooth surface on these moulds, being a low density board, we do have a much more porous and delicate surface than we would on a higher density board. And so unfortunately, we can't just treat these with a board sealer the way we would on those higher densities. Instead, the way to get a workable mould surface on this board is to coat the surface with an epoxy coating resin. XCR coating resin makes a great choice for sealing this board due to its fast, blush-free cure and excellent polishability. But the fast cure does mean a short pot life, so for larger surfaces or multiple moulds, you may need to mix in batches. Because we'll be using these moulds for resin infusion, it's crucial to seal the entire surface of the tool, not just the working areas. This is because it would be very difficult to get a release from unsealed board, even with multiple applications of release agent applied, and the bagging strategy I'm using means that resin is likely to track well past the edge of the reinforcement. It's important to keep the thickness of the resin to a minimum, especially on these mating flanges where the mould halves will come together. Anything more than a minimum amount of resin in these areas will prevent them from closing tightly and result in more resin tracking and an untidy seam or parting line. This has now been left to cure overnight, and the XCR has left us with a really hard shell-like surface. Now, the finish that we've got here, it isn't absolutely perfect. We do have some slight ripples and some slight nibs and imperfections. That is going to be how it is when you're doing a hand coating like we've just done. Now, you could spend a lot of time flatting into this and getting it almost perfect, but you will risk breaking back down through into the model board, and then you'll have to recoat again. And all of this could take a very long time, and that's really not the purpose of this process. This is all about speed. And so all I'm going to do is get rid of some of those nibs using a bit of 800 grit paper. Using such a fine sandpaper removes any risk of accidentally breaking through this thin resin shell, but will still knock off any small nibs that would otherwise transfer as low spots on the part. Next, several coats of Easy Release chemical release agent are applied to all the resin coated surfaces of the mould, including the flanges and the adjacent sides. Using a bit of board to shield the working face of the mould, some further protection from release problems is provided by RW4 spray wax, which is applied to these mating flanges and the sides of the mould. Amazingly, we're just a few hours of work into this project and we're already in a position to start making the component. But before we lay down the reinforcement, I'll just quickly explain the resin infusion process, why I've chosen it for this project, and what its compromises are. There are a number of ways you can make a component like this. The choice of process really depends on your available equipment, experience, and size of the production run. In the case of this monocoque chassis, we've got a split mould with fairly restricted and limited access, and we have a structurally demanding application. And this would normally make pre-preg carbon fibre the most obvious material and process. If you're not familiar with pre-pregs, I will add a few links below to some previous videos on the subject that should help to explain why this would be the natural choice. But with all that said, we're not going to use pre-preg for this part. Why? Well, the main reason is because of the moulds. Pre-pregs need to be cured at high temperature, and this means that they need high temperature capable moulds that are going to stand up to at least 100 degrees C. And unfortunately, there are several reasons why this epoxy coated model board can't be used in this way. Firstly, high temperature moulds need to be as homogeneous and balanced as possible. Any combination of different materials will result in different expansion rates at temperature, which is going to lead to distortion on the mould. Secondly, beyond 100 degrees C is beyond the service temperature of both the XCR coating resin and the underlying board. And these are going to soften at these temperatures, again leading to some distortion, and also potentially this coating resin could bond to the part, which clearly defeats the purpose of a mould. Finally, when used at temperature, these low-cost polyurethane model boards and tooling boards have a pronounced inhibiting effect on the cure of epoxy, meaning that they can almost never be used to mould epoxy pre-pregs from. Hence why the more expensive epoxy tooling boards are generally used with pre-pregs instead. So now we have pre-preg ruled out due to the high curing temperature, we can just look at ambient temperature processes. So now we have the options of a hand layup, which could potentially be vacuum bagged, or a resin infusion. Given that this part is a high performance component, hand laminating on its own with just a bucket and some resin without the consolidation pressure of vacuum bagging just isn't really going to cut it, as it would likely produce an overweight laminate with excessive amounts of resin and voiding, especially around some of these intricate details and contours. Vacuum bagging this wet laminate could reduce the resin ratio and the voids considerably, but the practicalities of wet laying this whole component, then getting it closed up, getting the vacuum bag into it properly inside the cavity of the mould, really would be highly impractical and almost impossible to do. And so that leaves us with resin infusion as the only practically viable process to use on moulds like this. Now, I'm a huge fan of resin infusion, and we've done lots of step-by-step video tutorials on the process, but never have I shown such an intricate part being infused using split moulds. If you've never seen the process before, put simply, this is going to involve putting dry reinforcements into the moulds, vacuum bagging them, and then draw the resin through using vacuum. Sounds simple, but let's see how it goes. So let's get started. We're going to start out with the hatch cover mould, as this is the simplest part in the project, and so I think it's going to be the easiest to understand the fundamentals of the process before we get on to the more complex ones. The first thing into this mould is going to be 2 plies of 210 gram twill. To avoid distortion and fraying of the dry carbon fabric when cutting and handling, I'm using the dual-purpose Fusion Fix EP, which both stabilises the cloth and provides a tack for the surface ply in the mould. Having a lighter tack than most spray adhesives is really helpful when trying to gently position this first layer. With the visible layer down, I'll use the tackier Fusion Fix GP2 to position the subsequent plies of reinforcement and core material, the core adding thickness and therefore stiffness to this long top hatch. The core material that we're going to use is this. This is Lantour Soric. This particular one is in 2mm, and if you look closely, you'll see these hexagons, and these are made of like a foam-like, non-absorbent material. And then around that, we have gaps around it that the resin can flow freely along, and then when it cures, we essentially end up with a rigid resin honeycomb going between the skins of our laminate. Now, this isn't the lightest core material you can use, but it does have the advantage of infusing very, very easily, and being so pliable, it's really easy to position into the mould as well. A light dusting of GP2 is all that's required to hold this super conformable core material in place, even into the quite tight curvature of this hatch mould. Although other infusion-compatible core materials like 3D core would result in a lighter laminate, they won't follow a curve like this, and so they're really only practical for less contoured shapes. Last is a final ply of 210 gram carbon fibre cloth to complete the reinforcement for this hatch. With the hatch laminated, we're now going to get onto the much more complicated split moulding for the main chassis. This will be approached in much the same way as we did for the hatch, so we'll be putting down reinforcement and core materials. But what I'm going to do here is do as much of this as possible with these moulds open, where I've got really good access into all of the corners for getting the material precisely positioned. And then we'll bring these moulds together, put in our extra pieces of reinforcement and core, and then set up the infusion through this area here, which is a bit more restricted in terms of access. Stabilising it again with Fusion Fix EP means that I can cut and position precise shapes accurately into the mould. These are followed by the first continuous ply of reinforcement, more 210 gram carbon, which is carefully draped into the mould and then spray tacked into position. In the detailed sections, the carbon would never normally follow these curves continuously, but this process of using a spray tack with some relief cuts makes it akin to using a pre-preg. Next, a second ply of 210 gram is added, with any cuts positioned so that they don't line up with the cuts of the first ply. More solid core material is cut, then positioned, which adds stiffness to the sides. Multiple strips of reinforcement are cut from some stabilised fabric, and then these are positioned around the edge of the core material, which builds up the thickness of the reinforcement in these areas. The core is then sandwiched inside another ply of 210 gram carbon. Next, the carbon fibre that's overhanging the edge of the mould where these are going to come together is cut down as flush as possible with the edge on both sides of the mould. Moving on to the nose cone, which is laminated in a similar way, starting by spray tacking a ply of 210 gram into each mould half, but this time the reinforcement on one half of the mould is cut with around 2 centimetres overhanging the edge of the mould. This is going to be used to join the two halves together shortly. We've now laminated these to the stage where they need to be bolted together before we can continue on and put in the last plies in the base and the joining strips. Now, one thing that's slightly unusual on these is I'm going to add these MDF plates onto the back of the mould. These wouldn't normally be needed, but because we've machined almost all of the way through the board here, it has become a little bit fragile and there's a chance that the vacuum bag might warp and distort it slightly. So adding these plates just stiffens that element up. So let's get the pins prepped and get them bolted together. To avoid the risk of resin tracking along the flanges of the split mould and bonding in these assembly bolts, I'm filling the threads completely with some filleting wax, which means that if the resin does find them, it shouldn't flow into the threads and lock the pins in place. Adding a bit more filleting wax where the pins come through the split flange should make it even less likely. The filleting wax is very soft at room temperature, and so these small fillets of wax around the pins will quickly squash flat as I gently tighten these moulds up. We will follow the same procedure for the nose cone, but this time I'm careful to ensure that the overhanging reinforcement on one side goes inside the other half and isn't trapped as the moulds come together. Being a smaller mould set with thicker walls, the nose cone mould doesn't need the MDF cheeks, but the rest of the bolting up procedure is just the same. Now that we have our moulds clamped together, you can clearly see on the nose cone that we've got this lap join. And once infused, this is going to bond together and become a very strong structure. However, you will remember on the chassis that we finished the carbon flush with the edge of the mould, and that's going to leave us with just a plain butt join, which clearly isn't going to be very strong. That's resolved by building up the floor here with a solid piece that bridges across. And actually, we're going to build it up solid to about 3 millimeters of thickness. It would be possible to put a core material into here, and it'd be relatively easy to do, but I've chosen not to because we have so many fasteners in the floor to attach the various parts of the car that a core material isn't ideal for this, as it's liable to crush locally when you tighten up a bolt. So we're just going solid there, and then we're also going to tape join the two sides at the front and back. For this thick, solid carbon fibre floor, I'm using a much heavier 650 gram 12K carbon fibre cloth, but stabilising it again using Fusion Fix EP so that I can accurately cut multiple panel sections to make up this solid floor. A total of 5 plies makes up the 3mm thickness of the floor, with each of the panel sections just lightly spray tacked into position. I've also cut some flat panels to reinforce the flat back section of the chassis. And then some strips of 650 gram fabric are used as a tape to bridge the join along the rest of the split line, again stabilised and fixed using some spray tack. Now that we have all of our reinforcement into the moulds, we can get on and set up our resin infusion. I'll talk you through every step in the process, starting out with this hatch cover, before we then move on to the much more intricate chassis infusion. First, some flash tape is applied to the unsealed outer edges of the mould. This is just to prevent any resin that tracks around them from bonding to it. Here I'm using ML3 infusion media. This is a peel ply and infusion mesh combined. Regular infusion mesh tends to spring up on tight curvature, whereas I know that the ML3 will be easier to tack down and easier to remove from these tricky corners. It is a thicker material, so I'm adding a few relief cuts where needed. Here, overlaps are absolutely fine, just make sure that there are no gaps. Positioning of infusion consumables like ML3 is best done with higher tack spray adhesives such as the GP2. Next, an infusion spiral is positioned down the length of one side of the laminar and secured in place with some duct tape. I then placed an infusion connector for the resin inlet at one end. On the opposite side, a length of MTI hose is cut to length, sealed at one end, and a vacuum hose is connected and sealed at the other end. And then the whole assembly is secured in place. The next step is vacuum bagging, and this is where the method of working with these temporary model board moulds is different from most infusions. Instead of adding pleats and taping the bag to the flange of the mould, in this case we'll be envelope bagging the entire thing. When doing this, great care needs to be taken when placing the mould inside the vacuum bag. With a padded surface underneath, the technique is to gently lift and tilt the mould and then work the bag along in stages. Never do this on an unpadded surface or attempt to just slide the full weight of the mould along the inside of the vacuum bag, as doing either is highly likely to puncture it. At the open end, the vacuum line is passed out of the bag and wrapped with a sealant tape before more tape is used to seal the bag around the hose. At the resin feed end, the bag is pierced above the connector and a PVC hose for the resin feed is inserted and sealed. The vacuum line is clamped off, and we actually connect the vacuum pump to the resin feed line for this initial pull down. This is because the MTI hose does severely restrict the airflow, and so it's just much quicker to evacuate the bag through the resin feed line to begin with. The bag pressure is pulled down in stages, with great care taken to position the bag into all of the tight corners and contours of the mould as the vacuum is slowly increased. Moving on to the trickier main chassis mould, the ML3 is cut into main sections as before, and then spray tacked into place. This is followed by some smaller infill pieces for the complex corners. Again, overlaps are fine here, but any gaps will create problems with the infusion. Flash tape is again applied to the unsealed edges of the mould adjacent to the infusion. Modelling clay is smoothed over the clamping nuts to ensure that they don't puncture the bag later on. This time, MTI hose is run in a horseshoe shape around the perimeter of the moulding. It's sealed at one end, and the vacuum hose is connected and sealed at the other. The resin feed spiral is run along the bottom of the chassis. This configuration keeps the maximum distance the resin will need to flow under 500 mm, which is about the maximum for this size of spiral and feed hose. Extra duct tape is added just to make sure the whole laminate and consumable stack doesn't fall off the vertical walls during bagging. Then the whole mould is carefully placed inside a very large vacuum bag. The reason for this becomes clear as the surplus bag is pushed down into the cavity of this hollow chassis. The resin feed connector is positioned on top. The open end of the vacuum bag is sealed around the vacuum hose, and again the vacuum pump is temporarily connected to the vacuum bag through the resin feed connector for this initial pull down. Vacuum bagging inside a shape like this requires even more care than usual to ensure that there's adequate bag to go into all of these tight corners without any bridging. To do this, it's really important to only increase the vacuum pressure gradually, allowing you plenty of time for repositioning the bag as you go. If you're planning a similar project to this yourself, don't forget that Easy Composites supplies all the materials and equipment used in this tutorial in both industrial and smaller quantities on our website. This includes the dry carbon fabric, the infusion consumables, the vacuum pump, and the oven used for the cure, available for shipping to most countries worldwide through the Easy Composites UK, EU, and US websites. Finally, the nose cone moulding is prepared for infusion in just the same way. This time I opted for the MTI hose around the perimeter, with the resin feed spiral feeding resin from the front of the nose cone. Right, now we're all bagged up, ready to run some resin into these parts. Normally for an infusion, I would use a standard epoxy infusion resin like the IN2, but for this project, I'm going to be using the EL160. The reason for this is, being a jet car, a lot of these parts are going to get hot, and the added temperature performance of the EL160 is going to be beneficial. Otherwise, IN2 would always be the recommended resin for infusion. The resin and hardener are measured out according to the datasheet and thoroughly mixed. The feed hose is secured in place, looping it through the mixing stick and taping the stick securely to the side of the bucket. And then the line is unclamped to start the infusion. Using the higher viscosity EL160 resin, the whole infusion takes around 20 minutes, which is well within the 5-hour pot life of this system. Once the infusion is complete, the vacuum line is clamped and the pump switched off. Then, a couple of minutes later, the resin feed line is also clamped. Next up, we have the main chassis moulding. With a similar maximum distance for the resin to flow as the hatch moulding, the chassis also infuses in around 20 minutes. With a shorter distance to flow, the nose cone infuses in around 10 minutes. With all the mouldings fully infused, they're loaded into an oven for an initial cure at 40 degrees C, which is only necessary as we use this special high temperature EL160 resin. If you were using the more conventional IN2 infusion resin, you would usually just leave it to cure at ambient temperature. Now that these parts have gone through their initial cure, we can get them pulled from the moulds. We do have to be a little more careful with these, as these moulds are a bit more fragile. Although the ML3 is easier to remove than conventional mesh and peel ply, it's still quite a bit of work, and tearing it all out, particularly in some of the tightest areas, took a good 20 minutes, and definitely wasn't the most fun part of this project. Okay, so these are the parts straight out of the mould, and for a complex infusion in very rapidly built tooling, I think they've come out really well. We do have an incredibly stiff moulding here. That's down to the fact we've got relatively thick laminate, and we're also utilising core materials in all the key areas, which further add to the stiffness. And because our infusion ran perfectly, we didn't have any leaks in the bag, we have managed to perfectly replicate the detail from the mould. Particularly, like, you can see this around the hatch rebate that we've got here. We've got no voids or pinholes, so this is going to finish up really nicely. But because of the rapid mould making method that we used, we do have some compromises. The main one that you'll see is a texture in the surface, and this is down to the coating that we put onto the moulds, which had some low spots, and that leads to some high spots. And so these should flat out really easily, and I don't expect them to cause us any problems in the finish on the final component. Now, the moulds that we used did hold up surprisingly well. There is, of course, a bit of damage where the wedges have gone in. That's because this board is very soft, and it couldn't be used to make lots and lots of components, but I would imagine that these could go on to make another 2 or 3 parts without any real problems. But for now, let's just get on and get these parts trimmed up. As usual, trimming is done using a permagrit disc in a rotary cutter. Here I've used some pinstriping tape to create a high visibility trim line. The trimmed edges and flash line are tidied up with a permagrit sanding block and finished with some abrasive paper before going back into the oven for a high temperature post-cure that the EL160 needs. After the post-cure, the final stage is to clear coat the parts, and it's this stage where we can correct the slight texture in the surface that resulted from the shortcut tooling method that we used. Using a DA and starting out with an Abranet disc and foam interface pad, the contoured surface is very quickly flatted to remove any high spots and provide a keyed surface ready for the paint. When flatting like this, wiping over the surface with alcohol or water is a useful way to check for any remaining low spots, as they're going to show up glossy. Painting is done using a specialist Phantom Clear carbon fibre clear coat, which is designed for pinhole filling and high build, but even still, painting a bare carbon fibre part like this to a pristine finish will require multiple rounds of painting and flatting. And so the paint is cured, flatted, and painted again, and finally flatted and polished to achieve a perfectly flat high gloss finish. With the painting finished, the only work remaining for us on this project is to drill through the solid floor and fit the suspension. So here we have the finished rolling chassis, and despite a bit of stress over the timescale and some sweat pulling off that peel ply, I have really enjoyed doing this project. And for one-offs or prototypes, machining a temporary mould like we've done for this, rather than the conventional route of making a pattern and then a full production mould, can save a lot of time and material cost. But don't forget that the moulds that we made can only be used at room temperature to make a maximum of 3 or maybe 4 parts. Using Resin Infusion has allowed us to make a high service temperature, high performing part without the need for high temperature moulds. Now, my enthusiasm for the Resin Infusion process is absolutely no secret, but even I was surprised by how smoothly the whole thing went on such a complicated layup. And we've produced a fantastically light, strong laminate with a perfect fibre to resin ratio, and no voids even around all of these detail corners. The whole process from the final design to the finished parts was fast, taking just 3 days of hands-on work, and it was also cheap, relatively speaking, with the total cost for the materials in this project coming in at under £1,000. To put that into some perspective, if we'd gone with machined epoxy patterns, pre-preg moulds and then pre-preg parts, I would guess the materials and labour would both be 3 or 4 times that amount. All in, I think that the combination of the tooling shortcut and the smart process selection worked well to achieve the objectives of this project. But do let me know what you think in the comments section. If you're looking for materials and guidance on any composites project, whether that's using the most advanced materials and processes available or how to hit a tight timescale or budget, Easy Composites have the materials and expertise to help you succeed. So please get in touch. The only thing left for us to do on this project was to take the chassis over to James at the Project Air workshop for him to fit out ready for the record attempt. To see his side of the build and find out how he got on, head over to the Project Air channel. To learn more about an alternative low-cost tooling method, check out this video on the Unimold rapid tooling system from our products channel. Or if you want to learn more about the Resin Infusion process, check out this video where we go through it in step-by-step detail. From everyone here at Easy Composites, thanks for watching and see you next time.